Okay, we're going to get started, everyone. Holden, it's good to see you here. It's my pleasure to introduce Holden Karau. I've known Holden for years. We have a really deep relationship, despite the fact that we've only ever met each other at conferences. And so I'm not
A
at all
lot of
surprised.
conferences, though, like a lot.
Yeah, lots of conferences. So Holden is a longtime Spark maintainer. She's focused on the Python community with PySpark in particular. And she's been a really strong ally of the Python ecosystem, both in her work with Spark and sort of as a longtime evangelist. What I really love about her work is that she reminds us to have a lot of fun with our work, and she sort of has this sort of constant sense of curiosity and exploration that I find really hard personally to maintain, and it seems to be really natural for you. So I'm really excited about this talk, and I'll pass it over to you.
That's a very sweet introduction. Thank you. And I will go ahead and share some slides. So we're going to talk about sort of the principles of distributed systems, mostly from the context of like data parallel distributed systems, but also we'll explore how these things are different and how they're built on top of other things. Clicky button. I'm Holden. My pronouns are she or her. I am on the Spark PMC, and this means that the lens through which I view the world does have a bit of a bias to it. And I actively do try and use other projects besides Spark. I think it's really important. But certainly my views are colored by the fact that most of my distributed system experience is with Spark. I'm a co-author of a few books on Spark. A more recent book that's not on Spark. Actually, the O'Reilly people, they sent me this very nice little thing of it. And I get more money if you buy this book. So definitely buy several copies of Cubiflow for machine learning. With your employer's money, with your own money, don't be silly. You can follow me on Twitter. And another thing that I try and do is code review live streams. And lately I've been also live streaming sort of my experiences working with different distributed systems in the data parallel space. So Dask, Ray, Spark, and I like it. And I really like when people come and join me. So if you're the kind of person who likes watching live streams code, please, definitely come and join me. Another important part is I am one of Timbit's moms. Timbit is my dog, and I love him. You will see him featured prominently throughout the rest of this talk, I assure you. And in addition to sort of like who I am in the professional context, I'm trans, queer, Canadian in America. I got a green card this year, so that was exciting, but I used to be on an H-1B work visa. I'm part of the broader leather community. And I think this is something that's important for me to talk about because to me, it's important that those of us who are working on open source data tools and really working on anything which is shaping where the world is going, it's important that we try and build diverse communities. And I think part of that involves talking about where we're all from and realizing that, there might be certain people who we don't see at the table who we should go and invite to our communities. And I think we're used to having those discussions around companies, but I think it's also important in the context of open source projects to have these discussions, right? And it's totally normal to start a project with a bunch of your friends who you maybe went to school with. But then as it starts to grow, it's important to make sure that you're not just getting more of the same people involved. And I think this is something that I've seen in the Spark community happen. And I'm not saying that we've addressed it in the Spark community. I think it's an ongoing area of improvement. And I think talking about it is one of the first steps that we have to do. So with that, let's get back to what we're here to talk about. So you are probably interested in distributed systems. If not, this is the last talk of the day. If you just like the magic black box that makes the code go vroom, that is totally cool, but this probably isn't going to be a super interesting talk for you. So feel free to zone out or bounce to something else. It's not like I can see people leaving the room in Zoom. Yeah, that's my dog again. And I'm hoping you're nice people. And that's if you're not, please don't take the time to prove that to me. So we're going to talk a little bit about distributed systems. We're going to talk specifically about data parallel distributed systems. We're going to talk about how they are different and how they're similar. And we're going to talk about how some of the choices that we've made that are common through things like Spark and Dask and Ray and even MapReduce have left us with some opportunities for growth and improvement, I believe is how a manager would phrase it, if they were being kind. And I think it's really important to know that like these tools, right? Like we're talking about them, and I'm going to be talking about some of their current drawbacks. But those drawbacks don't have to exist forever, right? Like these are all open source projects, and we would love to have more people working on them. Okay. So what are distributed systems? So I love Leslie Lamport's description of distributed systems. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And that is what I think of when I think of distributed systems. It's a bunch of different computers. If one of them fails, everything catches on fire, and I have a very sad time. And our job as people who work on improving distributed systems is to make it so that the failure of a computer you didn't know existed doesn't render our computers unusable. That's our goal. We don't always get there though. That's okay. So why do people choose distributed systems? So the main reason is fundamentally scale, right? It's often that we have problems that are too big to fit on a single computer, either in memory or it's too big to fit on disk on a single computer, or it would just be really expensive, right? Like mainframes, those things are not cheap. So it's often much more economical to use a bunch of commodity hardware. And sometimes it's not necessarily the size of the data so much as it is the complexity of the processing. And so the processing could take too long to do on a single computer. And the final one is making easy problems hard enough to be interesting. And I put this here slightly in jest, but also like, let's be real. Sometimes we'll take a problem that's pretty boring and we'll make it a little bit harder so that it's kind of fun. And that's okay, right? Like it is okay to have a lot of fun. Just make sure that you eventually get around to solving the problem you were trying to solve. And it can be a great learning experience sometimes. But certainly I've seen situations where this happens and then maybe, a few months down the line, it comes time to reevaluate and it's like, well, we have a 1 meg CSV file. Perhaps we don't need a yarn cluster. But, it's certainly an interesting learning experience. So what are the core building blocks that make up distributed systems? Fundamentally, you take everything in computers and you add the word distributed in front of it. Distributed locks, distributed clocks, distributed counters, which is, that's kind of a cheat. But I like to think of locks and clocks. And locks are important because when we have a bunch of different computers, we're used to race conditions that can happen with just a single computer and multiple threads, but those race conditions can get so much more complicated when we start adding, hundreds of computers, potentially each running their own thread pools or process pools. Keeping track of time can be important. It really depends on your system. For streaming people, distributed clocks are really important, ordering of events. Counting things is surprisingly hard. Especially in distributed systems. One of my big projects, which I still have not finished to this day, is to make reliable counters inside of Spark for counting data properties. And it turns out that is really, really hard. I've been trying to do that for a very long time. But because of how we do things specifically in Spark, making these distributed counters turns out to be really hard to do right. We do have distributed counters. They're not accurate, but it's often good enough, right? And that's one of the trade-offs that we make in Spark. So, okay, I've sort of been implicitly talking about data parallel systems without necessarily explaining them a lot. So let's talk about what some different classes of distributed systems are. So I like to think of them in sort of these broad categories that, everyone else will have their own categorization system. I think of file storage systems and databases as kind of separate, although the properties can be a little bit similar, and the lines between all of these things are a little bit blurry. But I think of like the Hadoop file system or S3 or MinIO, really anything where the data is split up on a bunch of different computers, and I maybe expect one of the computers to fail. Now, of course, we could be in the situation where something like NFS, right? And in NFS, it's like distributed in that many clients access the same data, but it's also not distributed in an important way where there's a single node which is responsible for the files of record, right? And that's sort of like a design trade-off, right? Like NFS, locking can be implemented a little bit easier, although NFS has some problems with locks. But doing the same things inside of HDFS or S3 can be even more challenging because we have multiple servers that are responsible. Another thing which I like to think of as its own class is embarrassing parallel. And it is kind of like a special subcase of data parallel, but things where there is really no coordination required. So the different workers don't have to talk to each other, right? Now there might be like a controller who is responsible for like handing out pieces of work and making sure that they get done. But the different workers, there's no data interchange between them. Embarrassingly, parallel problems are some of the, how would I say this? Most enjoyable because you can do all kinds of cool things to make them go fast. And that's really because there's this no coordination or minimal coordination. Databases, that's where things start to get really fun. Distributed transactions are scary. Cassandra, friends like this. And then, of course, there's different models inside of the databases as well. There's leader-follower replication, where like we might have someone who is always the leader and we elect the leader, or it might be a statically configured leader. But we have like a machine that is like designated to be the machine of record. And then we'll have replicas, which we can access data from, but for the data to be committed, it has to be written to the leader. Then, of course, there's more distributed systems where we have some kind of distributed voting, and then data has to be written to some percentage, and it's not a strict leader-follower kind of situation. Another one which I like to think of, which is a little bit different, is API servers. And this is because I started out my life building search and recommendation systems. And these are kind of like the read side of databases, I like to think of it. It's just like, well, not just the read side. My situation was only the read side because I was just doing batch updates, but your API servers can definitely also be having to do updates. But you have multiple servers, you have multiple clients, ordering, time, all these things, all of the sort of core properties that we think of in distributed systems, they matter. Now, of course, you can have an API server which isn't horizontally scaled. You can have it where you've got a single instance, but in that case, you're limited to what that single machine can process. And data parallel is the stuff that we're here to hang out with. Dask, Spark, all these friends. And it lets us ignore a whole bunch of problems, or not necessarily completely ignore, push those problems off to other specialized distributed systems. And that is really key because I'm not a file system engineer, right? Like I don't want to think about all of these problems. I can only hold so many things in my head. So what are some things that we get to ignore by working in data parallel systems? So unless we're dealing with streaming, we get to really ignore the distributed clock problem, timing and ordering of events. That's pretty chill. Network partitions, we don't get to like completely ignore them, but because we have generally the idea of a key controller node, if a whole bunch of the computers just get disconnected from that key controller node, yeah, our job is going to run slower and we might have to do some kind of fault tolerance thing, but we don't have the two generals problem. Multiple clients, of course, there are add-ons which make it so that you have to worry about this. For example, if you expose a Hive thrift server or you set up Livy, but generally speaking, you know, you've got one client at a time, and that's a little bit easier. Leader elections, this one is generally speaking, we don't directly have to handle the situation of leader elections. The leader or keynote is sort of defined in advance. And that's really cool. Of course, there are exceptions, like when you run in high availability mode, you might have Zookeeper doing the leader elections, but at that point, you've really pushed it off to another system anyways. So it's definitely not a core problem that we have to deal with. And then we also wave our magic wand, and we say this one magical keynote is probably not going to fail. And this lets us cheat with a whole host of problems. But there are some serious downsides. And there's a reason why, you know, the leader follower thing isn't what everyone does all the time, right? There's some pretty substantial downsides. But it's okay. We'll get back to those downsides and we'll focus on sort of the problems that we really can't ignore. They're the problems that we exist to solve, right? Dividing and coordinating work and data. And this is, you know, that's really the core of what a lot of these systems do. Reliability on machine failure. So that's the thing where, if we think back to that initial quote from Leslie Lamport, our goal is to make it so that the failure of a machine we didn't know does not cause our computer to stop working. Of course, once we allow state in, everything gets a little bit fuzzy. And there's also a sort of very loose definition of transactions that we have to care about. And that's because, like, we might be generating data and there might be a downstream consumer for our data. And we don't want that downstream consumer to be reading the data before we've completely finished writing the data. Or if there's two people that are both trying to write the same data, you know, that could get kind of messy. So that is something that we have to be concerned with. And then bottlenecks on the reliable or key node. Or leader, and that's, you know, it lets us cheat with all of these problems, but there's a downside of once we've got this magic box that we assume never fails, people like to put a lot of things in the magic box, and then the magic box starts to run kind of slow, and you start to lose all of your advantages of being a distributed system. So, okay, dividing work, like, how hard could that be? So it turns out that there's an entire class of people who spend a lot of their time dividing work. And that's with humans, where we can, like, use judgment. More seriously, with computers, it's really difficult, and for a whole bunch of different reasons. Sort of the classic problem of key skew. And that's this idea that we tend to separate work by key, but it turns out that, you know, as much as we love uniform distributions, data isn't distributed uniformly. Often it turns out a lot of people live in key geographic centers, so data about people tends to have skew, data about regions tends to have skew, data from computer has skew, null is a very popular place for computers to live, you know, all of those things. And even without data or key skew, we can have situations where we have non-uniform processing times. And that can come from a whole host of reasons, right? That can come from our algorithms taking different amounts of time to solve for different inputs, right? It could be data It could be noisy neighbors, because often we exist in a cluster where there are other processes running. And so some computers will be slower and some computers will be faster. And which ones are slow and fast will change dynamically over time. And just generally speaking, herding any variant of cats, dogs, humans, or computers is really hard. Now, of course, my dog is a Sheltie, so he will say that it's really hard, but it is a lot of fun. And it turns out that like he and I agree about this. We enjoy, trying to get things to go in the direction that we want them to go. Okay. Well, so we said we had to care about fault tolerance. So how do different data parallel systems handle fault tolerance? So sort of the initial classic way was very much there's another system that's going to handle fault tolerance for me, and I'll just put all of my data over their approach. And that it was the approach taken by Hadoop MapReduce. And it's very much the Hadoop file system, HDFS, is going to be my distributed file system. It's going to write the data out to a whole bunch of places. It will do a bunch of like fancy math and replication and figuring out what to do when a node fails. And I can just always assume that I can read my data back. So it doesn't matter if my executors fail. This is a bit of a cop-out because someone does have to make the reliable file system. But it's pretty solid. It is, however, kind of slow, because it turns out that writing data to disk is slow, writing data to 3 disks is slower, and writing data to 3 disks over a network with the JVM is really quite slow. And even with all that being said, while it is incredibly slow, Spark actually, and other systems like this, do frequently have some concept of something called like checkpointing, right? And that's the idea that like our primary system, which we're going to talk about in just a second, recomputing on failure, isn't always the right solution. Sometimes the right thing to do is to save the data to disk, and then if anything goes wrong, we'll read it back. And so it's not just MapReduce that does this, but I would say MapReduce was definitely the distributed system which popularized this approach. Recomputing on failure is probably the one that people here are most familiar with. It requires that we know how to recompute data. It has really bad implications if you've got any kind of state updates, if you've got actors that you're sending messages to or anything like this. It's not great. And while this was a great model initially, it sort of was based on the idea that failures are, yes, they happen, but they don't happen super frequently, and they're also independent. However, it turns out that the assumption that failures are independent was a optimistic assumption for a variety of reasons. One is, it turns out like computers are often stacked together in racks. And so this concept of like rack locality was introduced. And so we had this idea that we might try and spread tasks out so they were running on different racks. When you run in the cloud, though, they don't really tell you, what racks there are. And this also leads really nicely into the next point. When we run in the cloud, there's things called spot instances. Or even when we're running on Kubernetes or Yarn on-prem, we might get into a situation where we are less important. We're running at a lower priority setting than, say a job that has to report to the CEO, or an interactive job that's serving a query. And those can introduce situations where these previously independent failures actually become really correlated, and we lose a whole bunch of machines all at once. And also, another situation is dynamic allocation. And so that's the idea that like, yeah, we're going to store data in our executors. That's okay. When we start to get rid of these executors, though, this is now correlated with our loss of these executors, right? And that's correlated with the scale down event. And that's no longer independent. It's no longer just random. And triggering recomputes could actually get in the way of our goal for dynamic allocation to be able to scale down. And so there's a whole bunch of different approaches to handling this. I worked on one where we migrate data. Other ones are just like, hey, if a node has data in it that has been accessed within, X period of time, just keep it as much as we can. And that's just for dynamic allocation, though. Obviously, that can't really do anything about spot instances. Really, fundamentally, what it all comes down to at the end of the day is someone has to do a lot of math, and you have to have a few extra computers. And as we see, like generally speaking, in these situations where someone is doing some fancy math and a few extra computers, right? Like that's the HDFS layer. We're normally pushing that down to a layer which we don't have to directly care about. Someone else is responsible for building that fundamentally reliable system that we just take advantage of. And the last approach is just ignoring any faults. And this is an approach that is, it doesn't work. But very popular, I gotta say, very popular, and often implemented by accident. We'll implement something that we don't believe is going to fail, so we don't bother implementing fault tolerance, and then it turns out that it does fail, and then we have to figure out a fault tolerance mechanism for it. Okay, so one of the other points is, why do we have to care about state, right? Like, if everything's stateless, right? Like if there's no data, then I don't have to worry about losing my executors. Or, maybe I don't have to worry about losing my Keynote. Sorry, I need more coffee. As Snoopy says, I am allergic to mornings. So even when we're making stateless transformations, we have some state involved, right? And that's like keeping track of what records we've processed and which records we haven't processed. Generally speaking, we're processing data to do something with it, right? We're not just like processing data for the sake of it. We're processing it to like clean it up and save it out. And at those points, like, yeah, there has to be some state that exists, right? That state might exist locally within a single computer, but there is some state, and it's not that we can just like relocate these processes free of charge. I like to think of this as, I need to know if Timbit has had a bath this month, because if he hasn't, I need to give him a bath. And I can't depend on Timbit telling me that, because he's a dog and he also doesn't like baths, as we can see from this photo here. Okay, so just a little bit of state. We'll just sprinkle it on. So recomputation starts to become a lot more tricky. And fundamentally, honestly, none of us really do a great job of handling state. Actors and accumulators, all these things represent state in different systems. None of us do a good job of handling it right now. I would say often when you find yourself in situations where you are building up some kind of state, try and see if you can, put those rights out into another system. Do it as a transaction that gets rolled back on executor failure, right? Like, try and think if there's another way that you can do this so that you aren't having to be responsible for state, or you're not making a system which wasn't really designed for being responsible for state, responsible for keeping track of your state. And of course, the Spark approach is we put all of our state on this one reliable node and it gets sat. And so there's a few different approaches to this, right? One is that we can add something to restart that key reliable node on failure. And so all we have to do is hope that the thing that processes the thing never fails, but that might fail. So we'll just put another layer underneath it, and so on and so forth. And eventually someone deploys Zookeeper. And then unfortunately, the problem with this Keynote is because we decided we really didn't want to put as much state anywhere else in the system, we filled it up with a whole bunch of state. And so we have to actually manually write a bunch of code that tells it how to recover from failures. And this is painful. I would say that the approach that I see most successful here isn't recovering from failure so much as it is throwing away everything that's been computed and just starting over, right? Like, if we just view the entire pipeline as lost and start over, that tends to work out better than trying to do complicated, writing state out systems. Yeah, there's some downsides. Our Keynote does get very tired. It's often a central scheduler. Um, all of the state exists in this one Keynote. Well, for flexible values of the word all, and there's non-parallel components that sort of exist. Often you'll see that with things like gradient descent, where we like do some things, we bring all of the weights back, but we bring all of the weights back to one computer and then they get broadcast back out again. Okay, and so transactions. Transactions are hard, right? You know, there is a lot of research papers on why transactions are hard, but they're a lot less hard if you don't allow concurrency. Yay! Turns out, though, that people want concurrency, and specifically with things like Dask, we want to be able to write from many different executors at the same time. And one easy solution to this is to allow multiple writers, but the key central node is the committer, and that's the one that keeps track of all of the different writers, and on success will do some kind of operation to illustrate that the data is ready for use, the transaction is committed. And the Hadoop method of doing this was renaming all of the files. And it turns out that that was perfectly fine on HDFS and maybe not so great on S3. And the solution to that was to put a database on it. And that, if you're curious, you can go look at the S3A code. It has some ups and downs. It does tend to work though. And it works by making the rename not exactly quite a rename. Okay, so we've talked a lot about how things are similar. How are they different? So the APIs that are exposed by these systems is probably the biggest thing that impacts you as a user. You know, if it's not exposing the APIs that you want to use, it's probably not the system for you. Another really important one to think about is the level of introspection. And I'm not talking like, you know, do the developers go on a retreat and like ask themselves like, are we building a good system? I mean, is it able to understand what I'm asking? And by it, I'm referring to the distributed system. And there's upsides and downsides to this, but essentially, if things are being treated as black box functions, then the distributed system scheduler isn't going to be able to appear inside of our black boxes, and it's not going to be able to optimize them for us. So we really need to understand what sort of things the distributed system understands and what sort of things it treats as a black box. And this differs a lot between the different systems. Another one is the unit of scheduling. And this is related to how expensive it is inside of the system to schedule, right? Like if it's really expensive to schedule tasks, then you tend to pick larger units of scheduling. But if you've made it very inexpensive to schedule tasks, you probably pick smaller units of scheduling. The approaches to node loss are another really important one. There are slight variations in how this is handled, and that can make a big difference for you. And I think another really important one is community, right? I love the Python data community. And I think the different communities that exist for these tools can be a big reason to choose, you know, one tool over another. If, you know, I don't know, I don't like working with people that aren't nice, right? Like spend your days working with people who are nice. Life is too short to work with assholes. Or yeah, that's probably an okay word to say. It's not like I got a rewind button anyways. That's really all I had. I think the plan was for the second half hour to be more of an informal chat. But I wanna leave this for those of you who might not be joining the informal chat with, if you think any of these problems sound fun, come and join one of these projects. They're all open source. They all need help. You don't need to be an expert at distributed systems. You know, there are tons of things that can be done. Please come and join. If you're interested, I'm going to do some more open source live streams next month, sort of depending on my brain cooperating with me. And the last point is there's a saying in the ASF, community over code, and I think that's really important. And I think it's something that I have to remind myself of. And I think it's important for us all to remember that at the end of the day, right, people matter. You know, don't get into a like pissing match with someone over a 0.1% performance improvement. It's not worth it, you know. Cool. So let's hang out and chat informally.
Yeah, Holden, if some people might not be able to join us on Gather, do you have a couple minutes to maybe take some questions here?
Yeah, totally. I can do some questions on Zoom first, and then we'll bounce over to Gather. I'm going to stop the screen share, though, if it's okay.
Yes, that's fine. So yeah, if you do have a question, you can pose it in the Q&A little function there or the chat. We can see them in either place. So while people are thinking of a question and typing them in, I did want to put one thing from the Dask community is that while we have people here, there is a community survey that the Dask team has put together. So I'll put that in the chat as well. You know, this is a chance to, you know, give your little input to help improve the Dask community and Dask in general. So I'll put that in there, and then if anyone has any questions here, we can take them. And if not, if you want to wait to Gather, then we can head on over there as well.
I see a raised hand. I don't know how that works. Zoom is not my.
Yes. Jan, I'm going to let you talk. So Jan, if you want to ask a question. You should be able to unmute yourself now.
Sorry, it was a mistake. I did raise the hand by accident. I didn't have any questions. Sorry.
No worries.
No worries. We have one question. Any pointers in how to integrate Cubiflow and Dask?
Yeah. So yeah, that's a good question. I would say, so Cubeflow uses its own custom scheduling system. It's built roughly on top of Argo, although it has multiple different backends. I would probably look at Dask and Argo, and that would probably sort of be where I would start. But I don't know of anyone who's done a Dask Cubeflow integration just yet. But I know that there are some things for calling Dask from Argo, and that's probably going to be a good sort of jumping off point for figuring out how to do it from Cubeflow.
Awesome. Next question. Do you think Dask scheduler could be improved on many nodes to allow more load?
Yeah. I mean, so all of the schedulers could be improved, right? There's so many things. Yes. The Dask scheduler can be improved. The Spark scheduler can be improved. The Ray scheduler can be improved. I would say that the Dask scheduler tends to have much lower overhead than I would expect coming from Spark. But that doesn't mean that there isn't more room for improvement.
Yeah, and the follow, is there a right way of doing that, do you think?
Is there a right way to improve the scheduler? Oof. Well, I would say find the people working on the scheduler and talk to them about the things that they wish they'd done differently, and then help them. Yeah, I mean, that's an awesome project to work on. I think that's really cool. My other piece of advice would be maybe don't start in the scheduler, because that can be more complicated than other parts of the system, and I tend to find it easier to start a little bit further out, right? And then, keep in mind, that you do want to work on the scheduler, of course, but I would start with like fixing some bugs that seem maybe related, like race conditions or locking, stuff like that. And then work your way up to working on the scheduler.
We have a question. How did you get started with distributed systems and getting involved in those open source projects?
Yeah. So I was building search systems and recommendation systems at the time, and they didn't work very well. And so it was at Foursquare, which, throwback, the company still exists. I checked. So we won't go into too much detail. But essentially, the problem was like I was trying to build better search systems, and the amount of data that we had, I just couldn't process without using some kind of distributed system. We were at that sort of transition point from the ability to fit everything into one very, very expensive EC2 instance to no longer being able to solve our problems with buckets of venture capital. So that's how I got sucked into this. So fundamentally, I am trying to solve a problem from many years ago. I just got distracted along the way, which is very fitting for sort of who I am as a person.
Next question, where do you think Spark and Dask will be in 5 years?
Oh, that's a really interesting question. I suspect, okay, so as with everything, like these are my own personal views, et cetera, et cetera. My guess is that Spark will probably focus more on the JVM ecosystem. We've seen Spark try and make improvements for its Python stuff, and I've been a part of that. Like but I would say it's hard to see Spark sort of holding on to the Python analytics space long term. It could totally happen if Arrow integration ends up speeding things up a lot more, but it's really complicated to get shared memory systems right. So I wouldn't be betting on that. I would see Dask and Spark as probably coexisting. But I'm of course a little biased because I'm on the Spark PMC, and I would prefer to not have Spark completely disappear. It makes it a lot easier for me to have jobs.
The next question was from Julian. She says, hi, Holden. Thanks for your presentation. Smiley emoji. You said one needed some math for designs. As a math person, I am interested in knowing more. Is this about determining constants or about some optimization? Thank you for your insight.
Okay, yeah. So to be clear, I have a bachelor's of math, and I am solidly from the D's get degrees school of mathematics. So I am not qualified, but it is a fascinating area, and I do love reading the papers. Leslie Lamport has some really great papers. There are all kinds of papers also from Google. So there's a lot of stuff about essentially like not just determining like constant factors, but different ways of handling votes, different ways of handling network partitions, and sort of the trade-offs inherent in those algorithms. I would say if this is an area that you're interested in doing, one of the places to look is a lot of distributed systems have historically just said like, you know what, I'm just going to depend on Zookeeper for like all of my distributed locks or whatever. Like all of these things, I'm just going to outsource to Zookeeper. But People don't want to do that so much anymore for reasons that are complicated. So if this is an area that you find interesting, I would suggest looking at contributing to Zookeeper, or you could look at one of the many projects that currently uses Zookeeper that's looking at sort of bringing that logic in-house and trying to do it in a way that makes more sense for their specific use case.
We have a question. Are there any up and coming technologies and distributed systems you are particularly excited about?
I mean, I like Dask. I like Ray. I'm very fascinated with Arrow, which is not necessarily a distributed system technology per se, but I'm excited about it from the perspective of being able to use it more in distributed systems. I like Kubernetes in part because while Yarn has been a wonderful platform to build on top of historically, I think that there is certainly, Kubernetes isn't perfect. It has a lot of drawbacks, but they've managed to capture the interactive use case share of the market, and not for analytics, specifically like interactive, like API servers and stuff like that, web servers. And I've always sort of dreamed of not having to maintain two different kinds of cluster managers. And maybe this is an unreasonable dream, but I'm excited about us supporting that better. I would say that Dask and Spark and Ray all ostensibly have Kubernetes support, but all have a lot of opportunity for growth in there. I would say a lot of opportunity for growth. Unless my manager's listening, in which case Spark on Cube is amazing. No more questions.
Anyone else does have a question for Holden? Now's a good time to put it in there. And then when we wrap up, we can head on over to Gather. Question is, what about exascale?
Oh, that looks cool. I don't know. TLDR, it looks shiny.
Can it be reached easily with today's software?
No. No.
Well, Holden, thank you so much. I think I put the Gather link in the chat. So everyone who's interested, please join us there. It'll be a little more informal and we can kind of socialize and hang out.
Cool.
But no, thank you. Thank you very much.
Thanks so much for having me. It's really great. I'm gonna grab a cup of coffee before I come join Gather. So I'll be there in like 2 minutes. But I need my coffee.
Awesome. Thanks everybody. See you there.